Hey everyone, today I'll be talking about Radiosity. This will be probably a 4-video lecture series, and it's going to go over everything about the Radiosity method for rendering computer graphics. So let's get started. So, what is computer graphics, right? It's a process of, let me just write it down. We want to render a scene, given this information. So let's say we have, for example, we might know stuff about what surfaces are in the screen, or in the scene. What light sources. And also some maybe material properties of these surfaces. So these material properties, for example, could be absorption or how reflective a surface is. And obviously, when we're trying to render a scene, we want to know where the viewer is located. So location. Now, I'm going to talk about ray tracing first of all. So there's a popular method that many people have heard of, which is ray tracing. So given some scene, let's say some room X, right? And say we have some wall, right? So I'm just going to start. So say we have some wall, right? That wants to be in the scene. Then how do we depict that scene? Well, there's a point, right, in the scene. It has 3D coordinates, maybe X, Y, and Z, right? And we want to color that point accordingly. Traditionally, when we think about coloring a point accordingly and projecting stuff onto a 2D screen, how do we do that? Well, we might have, for example, a viewer, right? And they are looking in some angle onto some plane. So say this is the computer screen. And suppose that there's like a 3D object maybe somewhere that's getting projected. So let's just suppose a ball, right? So for this example, I'm just going to use a ball. And that ball, when on the computer screen, will have some circular outline. But how is this different from a 3D, right? How does the ball look 3D on a screen? It's not really solid, right? So I don't think color is exactly it. So color does not determine whether an object is 3D. You might think of the shininess, right? So really the big thing here is what determines a screen, what determines a scene to be 3D is going to be revolving around the lighting. So in this video you see me and you know I'm 3D obviously, right? But how do I look 3D on a screen, on a 2D plane? It's because I have different lighting sources that illuminate different parts of my body differently, right? So maybe objects closer to you are going to be a little bit more brighter. So for example, that ball might be an object, and there's some light source, let's say, I'm just going to draw a little lamp. Okay, and then it's shining a light. And say the object near, the part of the ball near the light source is going to be a little bit lighter, and everywhere else is going to be partly darker, and you might even see the shadow. Okay, that makes sense, right? So lighting determines how a scene appears 3D, right? So ray tracing, how does it do that? How does it determine, given some light source, how does it determine how that scene looks 3D, right? Well, each point you can trace it, right? So for every point, you can trace all the light sources from which directions are the photons hitting that one particular point. And you can do that for every single point, right? I'm just going to ray trace, say, to some other point here, and that point is going to be ray traced somewhere else, and so on. And basically for every single point in the scene, you can render an image based on this kind of configured interlocking rays idea. So that's basically what ray tracing is. However, you might expect that this is quite computationally intensive. So ray tracing is very accurate, right? But it's going to be taking a lot of computation to get an accurate and realistic depiction of your scene. So what's a better way? A better way, well, I guess because this lecture is on radiosity, you might just say radiosity, right? But how does radiosity work? So I guess this is what this video series is going to go over. This first part, I'm just going to go over some definitions, right? So I'll just list out some stuff. So definitions. We're going to be working in 3D, but because I can only write and it's going to be easier to, depict and present into 2D, I'm just going to be writing stuff in 2D. But remember, this ray tracing idea, this radiosity idea is going to be implemented in 3D, right? So define some room or some whatever your scene is. Let's say that's going to be a subset, right, of the real numbers, or like R3, so 3D space. And because we're only going to be on this computer screen, we're only going to be looking in a particular direction, right? And at a certain object or a certain amount of objects in your room. So if this is your room, or I'm just gonna put a little quotation mark because it could be anything, right? Then we're only going to be looking at certain objects in the room. So we're going to say some V belonging to this room. That's what we're going to be operating under. Next, we're also going to be operating under a certain amount of directions, right? We can't be constantly looking everywhere, right, at once. The viewer only looks at a certain direction to render a screen. So let's call a set of maybe directions a subset of our unit sphere. So maybe we want something like x squared plus y squared plus z squared, and let's say that's equal to 1. And let's denote this as S2, right? Then we want all the directions that we could be possibly looking in. Let's call that omega. Omega is going to be a subset of S2. And why does this make sense? Well, think about it in 2D first. So in 2D, we do have our x squared plus y squared. I'm just going to write 2D over here. X squared plus y squared equals 1. You can represent that as the unit circle, right? So something like that. Always draw your circle before you draw your axes, but oh well. And our direction is basically any from here, right? All the way, so from 0 to 2 pi. So for some theta here, we know that theta is from 0 to 2 pi. Similarly, S2, we have, I guess, 3 directions, and you can use that same analogy, right? And we're going to do this same thing in 3D. So we have 3D, and we have our unit sphere. Okay, and we can, let's say some omega in big omega, right? Omega can range from, well, think about it, we kind of did 2 pi r, so 0 to 2 pi. Maybe we want to do surface area here. So let's call it maybe 0 to 4 pi, because the surface area of a unit sphere is 4 pi. So omega is from 0 less than equal to 4 pi. Okay, cool. I guess the common notation for whatever omega is, we call this a steradian. And I will be abbreviating it as STD. Cool. Now, okay, so I'm going to go over maybe a bit more on how we might color stuff. So, for example, I'll just say coloring. So each point, right, each point is also, I guess, more formally known as triangles. So they're not actually triangles, but they're triangles because they do have an x, y, and z location parameters. So each triangle can be colored differently, right? So the first thing we might want to do is denote some kind of ambient lighting. So for some room, right, let's say we have this room over here. And for everything in this room, or wherever we're looking, we want to have some kind of ambient lighting that denotes like every object has this kind of coloring, right? Let's denote that ambient lighting maybe something like E sub R, E sub B, or E sub G, E sub R, B. And this is because, well, ambient lighting is going to be in 3 kind of color. So RGB, you can create any kind of color on the color spectrum from those three main colors, right? Depending on your intensity. And how do we distinguish what, like each point, how do we distinguish the colors of each point, right? Well, maybe we can assign each point a tuple, a 3-tuple maybe. So a triple of points, let's say, I'm just going to use a different color. So say this point, to have, assign it some values, maybe KR, KG, and KB. Now these triple of numbers, right, they're going to represent the reflectivity. So reflectivity. And for example, if the reflectivity is 1, it reflects all of the light. So if KR is 1, it reflects all of the red light. If KG is 1, it reflects all of the green light, and so on, right? So for example, if I do say, and ERGB is just the ambient lighting. Let's just example, maybe we want to say ERGB is equal to, say, 111. And say at some point, right, it has a reflectivity of 0, 1, 0, right? Now, how does the point look like in the scene, right? Well, it reflects all of the green light, and it reflects none of the red light and none of the blue light. And I guess some color theory stuff, it should be a combination of red and blue at the same intensity, so some sort of purple, right? So this point's going to look kind of purplish. Okay, that makes sense. What about light sources, right? Because this I guess idea only encompasses maybe just the ambient lighting, right? So maybe we have some kind of light source. So I'm just going to draw a little circle. And how does that light source affect every other point in here? Similarly, we can have that light source have some kind of ERGB where it emits that lighting, right? Let's say this light source has ER, EG, EB, and let's say it's D1, D2, D3, because we can have any, like D1, 1, 1, because there can be any number of Ds for the light source. It's because there can be multiple light sources, right? So we just denote them by subscripts of D. Okay, cool. Now, for each of these Ds, for every point, the light's not going to be hitting equally, right? As in, you can almost think of it as it's not going to hit the same, because if we do have a light, like for example, like some wall and this light source over here, the light's going to be more intense over here, right? Because it's perpendicular. What about over here? How's it going to exactly, how does a component really work over there? Well, if you do know some linear algebra or some projection stuff, well, you would know that it would be a factor of cosine, right? So factor of cosine theta, and theta is the how like the lighting hits with the normal vector of that one point. Okay, that makes sense. So I guess our final coloring equation might be something like, so we do have K R times, for every point we do have E R, which is the ambient lighting, plus maybe E R D1 cosine theta D1, and plus dot 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 dot. And we also do that have that for the green light and blue light. And there we go. This is our coloring equation. But it turns out that coloring, again, right, it doesn't really help us with, it only colors the scene. It doesn't really project stuff as 3D or not, and doesn't make a really realistic interpretation of a real scene, right? So that's not going to work. And this is where radiosity comes in. So radiosity, I guess our final goal for this series is going to be able to come down to solving one sort of equation. And that's going to be through radiative transport theory. That's the theory of how radiosity works. And we're going to try to solve this numerically. So we're going to have some assumptions, right? And I will be, some assumptions will be talked later because they will come up as we go. And for example, polarization, interference, they won't be really covered because realistically it doesn't really happen all that much. Although there are like ways you can incorporate them into the equations. Okay, cool. So maybe some assumptions here. I'm just going to write down assumptions. So let's assume that all particles travel at the same speed. So when I say particles, we're talking about photons here, and I'm going to represent photons as gamma. So gamma travel at and speed of light, right? So constant. Okay, and particles do not interact with each other, so they also do not. Also, particles may interact with the host medium, right? So when I say that, there might be smoke in our scene, right? So for example, if there was smoke, maybe the photons get scattered, right? Maybe they're traveling in one certain direction and the smoke particles interfere with them and they go off in a completely different direction. Radioactivity is actually really good at, computing this type of stuff. And also one really big assumption is that photons, right, the distribution of photons is in equilibrium. And that's really important. So basically what that means is the average number of photons leaving the scene and coming into the scene is going to be the same. And that's going to be important because it's a big assumption and it's true in general, right? Because photons are really tiny objects. There's so many of them, it's really hard to count per se. And one last thing, we want to also assume that photons, right? Photons, we know that they satisfy these two properties and distribution's in equilibrium, right? But we also want them to, you might want to pause and find out, right? The number of photons, they do need to stay in equilibrium. But the problem is, we also want to assume that they're steady state, right? And what that means, steady state is basically assuming that, say I shine a flashlight, we can't really see we're trying to assume that we can't see the object illuminating, right? So say I shine a flashlight at a rock. We don't see the rock illuminating over time, we just see instantaneous, so that's what we're going to assume. So also steady state. Okay, cool. So all of this will be combining into a couple equations throughout the video series, and y'all can stay tuned to learn more about radiosity. So if you guys do have any questions, put that down in the comments, like, subscribe, all that stuff. If you guys do have any suggestions, I would welcome that too, because I'm just starting out, right? Thank you, and I'll catch you guys on the flip side.